Okay, here we go. So hopefully we are going live. Yeah. Hi, everyone, and happy Space Week 2020. I'm Danielle, and I'm joined by my colleagues here at Black Rock Castle Observatory today to celebrate Space Week with a discussion about asteroids. If you're just joining us for the first time, welcome to the Black Rock Castle Observatory YouTube channel. We post videos here about space, astronomy, and what we do here at the observatory. And we also do live streams like this to discuss topics that are happening in the space world, all different topics, all different angles. And if you haven't done so already, if it's your first time joining us on the channel, make sure you subscribe to the channel and hit that notification bell as well. This way you'll get notified straight away when we post new content like this or when we go live. And if you are logged into YouTube and you're watching us at the moment through YouTube, then you can see there's a live chat there. So if you have any questions during the chat, we would love to answer them for you. We've got some lovely experts here live to answer your questions for you. And we're going to start off by talking about asteroids and what they are. Then we're going to get into their impact for life here on Earth. And we're going to talk about the DART mission, which has been in the news a lot lately. And it's really, well, I'll let Alan talk about that. And then we're going to finish off talking about somebody who was actually hit by an asteroid. We'll get into that a little bit at the very end. So I would like to introduce my colleagues here. I am joined by Alan, who is resident astronomer here at Black Rock Castle Observatory and co-founder. I have Dr. Niall Smith with us. I always say Dr. Niall Smith is so formal. I have Niall with us, who is co-founder as well and head of Black Rock Castle Observatory. And I have Rob, the bio guy. So, right.
Hi, guys.
Rob's going to talk to us a little bit more about more of the life aspect and how the impact of what kind of impacts the asteroids have for life here on Earth. So let's get into it. Let's talk about asteroids. And first of all, what is an asteroid? Because I think there's a lot of talk about asteroids and meteorites and meteors. And so like, what's that difference between all of that? Niall, would you like to start us off?
Sure. Yeah. Thanks, Danielle, and welcome to Space Week 2022, as you say. It's great to be on this. So when the solar system originally formed, it was made up of a lot of pieces of material, from grain size to boulder size to size of cathedrals to ultimately then push it all together into the size of planets. But some stuff for various reasons was left behind in the making of that material. And so largely rocky material, which didn't basically end up as part of planets. And so these have become objects which we now refer to as asteroids. So asteroids are largely devoid of water. They do have some water, and we can maybe get that into that in terms of bringing life to Earth. But they're largely rocky. They're loose aggregates, so they're held together generally by gravity, but only quite loosely by gravity. And a big difference between them, for example, and a comet that people will be familiar with is asteroids don't emit enough gas material to form a tail. So although they may be, some of them may come close to the sun, they'll warm up, but they don't develop that tail that would be this, but that we would be familiar with comets. But the two are kind of both from the early building blocks of the solar system. And in the case of asteroids, for the most part, that refers to objects which are kind of close-ish to the sun and the Earth part of the system. Whereas in many instances, comets would come from a lot further away. So comets might even appear from well beyond the solar system in a region called the Oort cloud. So something that is postulated, but we've never actually directly seen it yet. But so that's kind of the difference between asteroids and comets. They're cousins of one another. If an asteroid, now you mentioned meteors and meteorites, so we'd all be familiar with shooting stars. So a lot of the debris, which may have been ejected by asteroids, it may have been ejected by comets, or it may simply have always just been floating around there on its own, since the formation of the solar system, or it might have been thrown out when this large planet collided with Earth and formed the Earth-Moon system 4.5 billion years ago, whenever. But a lot of that debris in the solar system is very small. It's just like dust particles. And that's what you see as a streak of light in the night sky. When it collides with the Earth's atmosphere, you get this sort of superheating effect because it's tens of thousands of kilometers an hour between the Earth and this piece of dust. And it just gets heated up by interaction with the Earth's atmosphere. And you see that as a flash of light. If it's big enough, then as it's burning up, it doesn't burn up completely before it actually hits the Earth, in which case we call that a meteor. I should have said the other, by the way, the shooting star is a meteor. If it hits the Earth, it's a meteorite. So if we reach the surface of the Earth, it's a meteorite. But just as a final comment on this bit, it could come from a comet, could come from an asteroid, could just be hanging around there. The meteor is if it burns up, meteorite if it hits the Earth. And obviously when it hits the Earth, that's when we all start to worry. And maybe we can talk a little bit about that during the course of this. So that's kind of a very quick summary of asteroid versus comet versus meteor and meteorite.
Yeah, and you're right. That is when we start to worry about it, is when they are hitting the Earth. And some of them we don't have to worry so much about. We've got some examples. Rob has one there. So sometimes they're just very small.
Yeah.
Don't have to worry too much. That didn't do any real damage to anybody, hopefully. And so we will get into the larger ones, and that's exactly what we're here to talk about today. So we've got some very large asteroids out there that are not the size that you could just fit in your hands, like what Rob has there. And we have evidence that they have hit Earth before, very large asteroids, right, Rob?
Yeah. So the most famous is probably the one that caused what we call the KT extinction event, and that's basically one that hit around the end of the Cretaceous period that famously wiped out all the dinosaurs. But not only did it wipe out the dinosaurs, not all non-avian dinosaurs, we still have a few of them with us in the form of birds, but it wiped out about 3/4 of all life on Earth. So there is a pretty significant impact of these things. If we look at it a bit too closely and start panicking, we might think, oh God, if that happened again, it's not the impact itself though that you really need to worry about. A lot of life did die during the impact itself, but it's the impact that it had on the Earth afterwards, the climate change that came about as a result, that we really needed to worry about, which gives us pause for thought today, because a lot of those impacts are things that we can kind of see around us, rising sea levels and crop failures and mass migrations as a result of people trying to get away from the impacts of climate change. So it's not completely alien to us, the world immediately after an asteroid strike. Not quite as extreme as it was 65 million years ago, happily, but it is still, food for thought. The one that hit the Earth when the dinosaurs were wiped out was about 15 kilometers across, so much, much bigger than the little ones we can hold in our hand. And it led to a massive crater in around Mexico called the Chicxulub crater. I do hope I'm pronouncing that correctly. But it's not by any means the only asteroid impact that we've ever seen. And we've even seen some in quite recent times. In 1908, the Tunguska asteroid didn't actually impact the Earth directly, but it exploded over Siberia. They still call it an impact because the explosion was enough to wipe out about 2,000 square kilometers of forest in Siberia and killed quite a few reindeer as well, but there doesn't seem to have been any major impact on people. More recently,
but Santa, poor Santa.
I know, right? No wonder Rudolph has a red nose. But more recently, we saw in about 2013, I think it was, in Russia, another airbush that was much smaller. It didn't flatten any buildings or trees or anything, but it did knock out quite, I think something like 1 million windows and injured hundreds of people. So it's not completely unheard of to have a large impact felt from a meteor, but it is very rare, I think, in terms of more everyday occurrences like shooting stars, etc., to actually have one impact us here on Earth and cause any kind of damage.
Yeah, so when we have these massive impacts like this, they are, if they're very, very large, then we're able to actually detect them. So one of the things that we have now that the dinosaurs didn't have is that we have space agencies, and we have equipment where we can look out into space, and we have telescopes where we can see some of these asteroids, and they're not very easy to spot. Is that right? I know you've gone out, and even with Big Bertha, have you actually imaged asteroids with Big Bertha?
Yeah.
What do they look like?
They actually, from looking through a telescope, they look very similar to another star. They're moving with respect to all the other stars, but other than that, they look pretty similar. It's just a white dot moving across the screen. Very different in how it moves across the screen, but very similar in its actual physical appearance.
For anyone who has not heard us talk about Big Bertha, that's the telescope here at the top of the tower at Black Rock Castle Observatory. So that's a very large telescope. But we have much larger telescopes in other areas that are now tracking these sorts of objects that are coming near Earth. And it's really important because we've never had the capability, well, hundreds of years ago, didn't have the capability to be tracking things like this. And if we aren't tracking them, then we don't know what's a threat and what's not. So we do have things set up. Even NASA has planetary defense. So this is a relatively new thing in terms of the existence of humans, but it's a big deal because, like Rob said, we do have these large impacts that do happen here on Earth and can wipe out life and alter life big time. So we have the capability to actually try and prevent this from happening. We don't want to have a massive impact at the Yucatan Peninsula like what wiped out the dinosaurs. So NASA has gone and done their very first test with the DART mission, which was, well, one of Alan's favorite things ever. He couldn't stop talking about it around the office and texting me. And I woke up at like in the morning, I don't even know what time it was, but here's a video of DART. It's a really cool mission. So the DART mission, DART actually is an acronym for the double asteroid. Oh, I always get that. Redirect. I always say redirectional and it's not. The double asteroid redirect test. So it's the first time that NASA has decided to try to alter the path of an asteroid. And this is important because we've got a couple options when it comes to how do we protect ourselves from asteroids. One of the ideas was, do you send a nuke up there? If anyone's ever watched Armageddon, do you just blow it up into smithereens? Problem with that is then you have lots of other asteroids you have to worry about. It doesn't completely obliterate the particles and make them very small, so where they're not dangerous for us. If they just end up being chunks, they still could be dangerous for us. So another option is let's try to nudge it out of the way, and that's essentially what the DART mission was, right? So do you want to tell us a little bit about DART and your expertise in the DART mission?
Sure, absolutely. And it was 7 minutes past midnight when I was texting. Because that was the live feed actually from DART itself, which was pretty unique.
He's the reason I have a do not disturb on my phone at night.
So the DART mission itself is actually a joint mission between NASA and the European Space Agency. So DART was a mission, as you mentioned, Danielle, to effectively see how we could change the direction of an asteroid. This is actually a double asteroid system. So it has Didymos and Dimorphos, two asteroids. So we were hitting the smaller one. So we wanted to see, basically by looking at how the light from this particular asteroid changes with time, because the moon is going around it, it kind of dims slightly. And by looking at how it changes before and after impact, we can see whether or not what's called a kinetic impact is going to actually change the orbit of only that moon with respect to, it's called a moonlet, only that moonlet with respect to the actual larger asteroid.
Sorry, let me just clarify. When Alan's saying the moon, he's not talking about our moon.
No, not our moon. That's why I said moonlet.
Yeah, that double asteroid system is a large asteroid and then a slightly smaller asteroid, and they're their own little system. So when you're saying moonlet, it's actually another asteroid that they're impacting.
Correct. So yeah, they basically smashed DART into Dimorphos, pretty extreme speeds with 25,000 miles an hour and whatnot. So there was a pretty serious impact. Much larger than they thought it was going to be. By the looks of it, by something that's small and that's far away. So it's billions of kilometers away from us. So it's quite small in the night sky. You wouldn't see it with many telescopes, although some telescopes on the European network actually have managed to image the asteroids themselves, as has the James Webb and the Hubble telescope have also imaged it.
That was a big deal. That was the first time these two telescopes have been able to collaborate on something and observe it at the same time. So there was a lot happening with this DART mission. Yeah,
and the impact looks to have been very significant. So there's a lot of talk about whether they're still analyzing. Let's just be clear. This only happened a couple of weeks ago. So they're still waiting for it all to settle, and they're still going to be using ground-based telescopes to actually continue to look at this particular object. So it's going to take another few weeks before the data comes in to see what the full impact of this actual impact was. But we still can image it. So the images that we're seeing are basically a tail, kind of not too dissimilar to what Niall was describing with comets and a tail. You can actually see what goes from a star-like into an actual, looks like a comet, and then back to a star. It develops this tail, and then the tail shrinks. And that's all from the impact of the DART itself. Just before it actually impacted the asteroid, it actually released, and this was one of the European Space Agency's contributions, it released a small CubeSat, an Italian CubeSat, which had an imager on it. So that also filmed the impact. So they're still analyzing those images as well. So they have both a lot of image data that they're still analyzing. So October is going to see a huge amount of new data come out on that particular impact. And it's also going to inform the next mission. So the next mission is Hera. Okay, it's the European Space Agency mission called Hera, and that's going up in it'll arrive at the system in 2026, and that's going to do much more scientific analysis of the actual impact of the crater impact. Although there's no concerns that they may have actually just knocked off an entire chunk of the moonlet. They're still trying to figure that one out. So they may have actually, created a massive event, much bigger than they thought. But going back to what yourself, Danielle, and what Niall and Rob were saying, they are trying to figure out what is the best method of actually pushing something off course, because there is still a lot of misunderstandings, but also misconceptions about the best way to actually protect our planet. This is all part of a planetary system, defense system, which NASA and Europe are collaborating on. So at the moment, what we're looking at is kinetic impact. So try and nudge it off course by smashing something into it. But that's not the only way. There are various ideas about attaching light solar sails to it and pulling it off course and using other redirection methods. The nuclear option is still on the table. Whether it's ever used or not is another matter. It's still directional. Nuclear propulsion is another method that has been looked at and continues to be looked at. But at the moment, the significant focus is on this whole impact side of things, and trying to nudge it off course by just hitting something into it, and seeing if we can get it early enough before it gets to us. And we can just a tiny bit of a nudge when it's further out means it'll completely miss us. The closer it gets to us, then the bigger push it needs, and that creates a problem. So that's why having observatories around the world continually monitoring the night sky is very important, so we can catch these particular asteroids and comets as they move around the night sky. Asteroids in particular, because as Niall said, they don't leave a tail, so they're much harder to actually see. So we do need to keep an eye out for them more so.
It's a good point that this mission, it is a test, and because this is a system, an asteroid system that's not really a threat for Earth. It's close enough that we can do ground-based observing and see it, but it's not a threat like what happened with the dinosaurs. So this is a good one to test on. If we nudge it one way or the other, it's not really going to come back and end up hitting us, hopefully. But there are things out there that we are watching. Like there is an asteroid called Apophis, and this is something that we've been monitoring and watching its path and seeing where it's going and tracking it, because it will come very close to Earth, and it'll be in 2029, it's going to be passing by Earth. And so there is an area that we call the keyhole. It's kind of like this lima bean shape, that if it passes through this keyhole, The next time it comes back around, it will impact Earth, and that will happen in 2030. It's 6 years later. So if my math's right, 2035. The best part about this is that if it does hit that key, this is not a good thing at all. If it does hit that keyhole and it impacts Earth, it'll happen on a Friday, which happens to be the 13th. It's a Friday the 13th. You can't make this stuff up. So yeah, let's test this out now. Let's test this out on something that's non-threatening, so that if we do have something like Apophis that ends up being threatening, that we can employ something like this in advance, years in advance, to just slightly nudge it outside of the keyhole, make sure it doesn't hit us. So that's the kind of stuff that we're looking at now. Have you guys been watching the DART mission?
I have, and I do think it's funny, just to briefly mention something regarding what you just said about watching the guys that are coming in. The most recent one that did impact over Russia happened while we were looking at a different asteroid that was coming close. So it was a couple of hours before the big one we were looking at was supposed to fly by. So it kind of snuck in under the radar. So very important to keep an eye out. Yeah. I did notice, though, I was looking at some of the facts and figures regarding DART, how fast it was traveling, etc. It was traveling at 22,000 kilometers a second. So that, I think that's like, it would go around the planet in 2 seconds. So it's a vending machine traveling that fast. Now, Niall, do you know if we can like get something to travel that fast quickly enough to impact something that's much closer to us? Or is this one of those things where we just need to know where it is from quite a distance out and act very early?
Yeah, I think so. There's a couple of things in that, Rob. So as Al mentioned about the whole sort of kinetic side of things. So there's two things about a kinetic impact, three things about a kinetic impact. First of all, the object that you're hitting, there's no point if you're going so fast, you just punch a hole through it and you go right through it and out the far side, and it effectively, you don't do anything to it. So you need to transfer the energy from whatever your spacecraft to that object, and in the transferring that energy, move that object slightly. So one of the tests of DART was, for example, to see just how well Didymos hangs together as an object and whether or not it would fracture. And the first indications that Al says is that it seems to fracture maybe a little more easily than we had kind of hoped, because that's potentially problematic. Not for it, because as Danielle says, it's not going anywhere close to us. No one needs to worry about that whatsoever. But in terms of getting up, so to get impact, you want three things said. You want to actually the object to be solid enough for an impact to be effective. The second thing is you want to have the spacecraft itself needs to be, like you said, a kind of a big fridge or something that needs to have plenty of mass in it himself. So you don't want a spacecraft that's so light that when it hits it, it's just going to go on the surface and that's it. So it needs to have mass. And then the third thing is it needs to have velocity, as you said, or speed in this instance. So the faster you can go, the more kinetic energy, and the more of that kinetic energy you can transfer from the spacecraft to the object, the more you can nudge it. So, and it's that balancing act of not trying to shatter it or punch a hole through it, or being so little that it doesn't do enough. And so we really don't know in practical terms what's the best speed and all of that type of stuff, and what's the best kinetic energy. And to be honest, Rob, it's probably going to be different for each asteroid. So we're probably always going to be guessing a little bit, because some of them are probably like, you take a stone from the beach or something that can crumble in your hand or something, and you take a big igneous rock. I'm not a geologist, and like the one you're holding or whatever, it's just not going to break up. You can't squish it with your hand. So it's pretty solid. So we know that asteroids come in all sorts of shapes and sizes, and more importantly, rather than shape and sizes, how well they're held together. We just don't know how well they're held together. So, but it looks like there might be quite a variation of that. So that gives us all sorts of interesting issues, because we could have a mission ready to go and it's the wrong mission. So we really need to think about this really carefully and plan for the future. So in terms of getting up to speed, just to actually get back to your question, Rob, you're absolutely right. It's like if you're accelerating a car. To accelerate a car, people spend an awful lot of money to get their car to accelerate faster than the car next to them. So trying to get up to a speed quickly requires a lot more energy than building up to that speed slowly. So exactly what you say, that at the moment, really, if we don't see these objects around, say, Jupiter distance or something like that, the chances of us A, being able to launch in time, and B, having sufficient velocity once we get there, because we may actually have to go around the sun and use the sun as a slingshot. So we use kind of the gravity of the sun to fire the spacecraft back out rather than just use the propulsion system that's on the spacecraft itself. So all the spacecraft we have that have gone at really high speeds, the like of the fastest, the Horizon spacecraft, they've all used these gravitational slingshots to get the speed up. So we give them enough speed to get away from the Earth. But that's only sort of, kilometers per second. And now we need to get up to these sort of very high velocities, really, to get enough energy. So it's actually very complicated. And so why Alan and Danielle and yourself have been mentioning the importance of looking at the sky, trying to anticipate in advance. And that's a big challenge, because these objects are potentially very hard to see. But just in case I don't get a chance to say anything else, we wouldn't want people listening to think that this is a problem that we're worried about. We're much more worried about, climate change and all that type of stuff, because even the keyhole, I think Apophis, probably got the name wrong now, is going to miss that. That's all the evidence is, that it's not going to hit us in 2035 on Friday the 13th or otherwise. So we're not actually, DART isn't a way to try to protect us against a known collision. If you look at it, there's no known collisions, I think, in the next roughly 100 years anyway. So you could ask, why don't we know what's happening in 200 years' time? And there's two reasons. One, we don't know everything that's out there. So things might interact a little bit gravitationally with other things that they come close to. But more importantly, or more likely, that these things called non-Newtonian effects. And non-Newtonian effects are actually really not non-Newtonian at all. But they're things like outgassing. So an object might be coming towards the sun, happily in its orbit, and then it warms up a little bit and a bit of gas gets expelled. And so it changes its orbit a little bit, just like a thruster on a rocket changes its orbit. We can't predict that. So we can't know that these, if they were just solid lumps of rock doing nothing else, we would know them for millions of years into the future. But they're not solid. They, so they're gaseous. They may even crumble. They may, heating and cooling, they expand, they contract, so a bit might break off. And now suddenly that just changes the orbit a little bit. So within a couple of revolutions, they're now, maybe coming close to the Earth. But we're pretty sure that for the next 100 years, we're safe of anything that looks big enough to cause us sleepless nights. Now, as you pointed out, we've had one or two that have been smaller than that if you're directly under it, it's just going to be a bad day for you. It just really is. So you just got to hope you're not under it or not going to get hit by it. But the chances of that happening are so small that nobody needs to worry about it. We have a lot, much more to worry about. But in the long term, planetary defense is all about making that probability zero. So it's small, but it'll happen eventually. It's not going to happen in the next 100 years. So we've got some time, and that's why the likes of DART is a good time to try to figure all this out before it's a screaming emergency that we have to worry about. So we're not in that situation as a planet at the moment.
Yeah. So we have had a few cases, like Rob mentioned earlier, of documented impacts here on Earth. And one of them is quite interesting. The only documented case that we have of something hitting a person was Ann Hodges. Do you want to talk a little bit about that, Rob?
Yeah, it's a really cool story. There's a woman, I think it was in 1954 in Alabama. She was struck directly by a meteorite. Directly. It came through the roof and bounced off of her radio and hit her on the side, and it gave her a pretty nasty bruise, but she lived to tell the tale. And we will be doing a small exhibition on her towards the end of November, along with colleagues we have in the University of Alabama, University of Limerick, Crawford College of Art and Design. Too many acronyms to be remembering, so sorry if I left anybody out. But it is really a very fascinating story. Now, I know a few people around the office here have been hit by meteorites as well, but that's just because I was throwing them a bit too haphazardly and asking them to catch them. Do we happen to have the model nearby?
Yeah, and I was going to say, so Rob has a few of the meteorites. We've got a few in the office as well. And you can tell these are not very large, but they would have been larger coming through the atmosphere. And as they come in, when you, like Niall mentioned, shooting stars that you see in the atmosphere and in the sky at night are usually these just breaking up into smaller pieces and that burning up. And what's left when it hits the ground is this. So this is actually quite large, right, in terms of like finding actual material on the ground. But what hit poor Anne is quite large. This is not actually what hit her, but this is a cast of what did. But could you imagine that? coming through to your house and you're sleeping in your bed and this comes crashing through and hitting your radio and then you. And like Rob said, if you get a chance to even just Google this poor woman, there's pictures of the side of her and it really did a number on her. Like this is quite and it's heavy. Well, I don't even, it's probably the real one's probably even heavier than this because these are mostly iron. So even this is a very heavy piece of rock. And when people touch the small ones, they usually go, oh, wow, that's much heavier than I expected it to be. So I can't even imagine what poor Anne felt being hit by this. It's awful.
And they're also really smooth. If you haven't had a chance to touch one, like I said, we'll be having an exhibition later in the month of November, and hopefully we'll be able to let you handle some of these. But you can feel how smooth out there by passing through the atmosphere. It's really, really cool. But as Niall said, in terms of existential threats, I mean, a pretty large asteroid hit a woman and she survived. There are much greater existential threats that we need to worry about in the short term. And
actually, Rob, as you say, like, you know, she was badly bruised and she had it's well worth looking at Anne Hodges because she had a very unfortunate life subsequently, which all started with being thrust into sort of the public eye and not everybody, you know, that doesn't go well for everybody. And she ended up with various stresses and so forth. So it's a separate discussion, but you're absolutely right. Like she's the only one who we absolutely know got hit and she didn't die. So it's just very rare. And actually, you know, it's becoming less rare, we think, in any way, because small stuff hits things or burns up in the earth or hits the moon or gets sucked up by Jupiter or whatever. So there's less and less of it, not more and more in our solar system. Our solar system is cleaning itself up. The dinosaur 65 million years ago, that's still relatively recent in terms of sort of the solar system timescales, but there would have been a little bit more debris floating around the solar system at that time. If we go back several hundred million years or a couple of billion years, we know that the early Earth would have been hammered all the time by massive things. So, you know, really one of the things, it's remarkable that early life probably existed in a period where the likes of the KT collision that hit us for the asteroids was relatively common, but early, very small bacterial life and so on managed to cling. It's only when you get sort of sophisticated, like you and me, I'm going to put us out there as being sophisticated, that we are much more fragile because we're, you know, something that's more complex, a more complex microorganism needs more to survive. A very simple organism is very resilient, and it does seem that when life gets hold on a planet, it's very hard to get rid of it, but it's actually getting there in the first instance. Of course, we still only know of the Earth as being the only place where there is confirmed life. So, yeah, that's also something which is for maybe for another chat.
Yeah, we're very lucky here that we do have a nice atmosphere that protects us from a lot of those threats as well, because the smaller ones could be more impactful if we didn't have the atmosphere to burn them up. So when you do look at things like, it's very obvious looking at the moon, it takes on impacts and it's had loads of impacts. And we do have craters here on Earth as well that are out in the desert and things like that, where we can see large impacts from asteroids, but we are very lucky here on Earth.
Yeah, we've even seen, Danielle, I mean, the likes of James Webb has already been hit by effectively, you know, space dust or whatever, but it is just natural floating around the solar system. It's not something that we've created. James Webb is 1.5 million kilometers from us anyway. So there's stuff floating out there. As you say, if you're an astronaut standing on the surface of the moon, there's a higher probability, because as you correctly point out, there's nothing to stop the dust being burnt up. There's no atmosphere to burn it up. So these are risks which we have to consider when we go to the likes of the moon, or indeed Mars, where the atmosphere is now frozen out. So there's really nothing to protect you from relatively small debris, but traveling at high speed. Again, very unlikely that it would hit you, but the Earth's atmosphere does a fantastic job of almost reducing that to zero for those of us. As I said, it'd be a really, really unlucky day if you end up being the first person on record and having your life ended by one of these things, you know. So I'd say it's just probably not the scientific way of phrasing, but it's just not going to happen. So nobody needs to worry about it. And I hope I'm not proven wrong on the probabilities there.
Yeah, let's hope that one's not proven wrong.
You don't want to be misquoted saying it.
Yeah.
But again, there is no known threat at the moment that any of us should be concerned about. More interesting to also examine these. I mean, one of the things that DART will do is allow us to understand more about how maybe asteroids are formed. That'll help us understand more about how planets are formed. That'll help us to understand a bit more about how life maybe gets brought to to Earth, or how it originated on Earth, or what was the whole interplay and so on. A lot of stuff we don't know. So it's fascinating to try to, once you start smashing things into something else, you always get interesting data, and that's what DART has done. It'll be really interesting, as Al says, to see what's coming through in October, November, and December, and so forth. So,
I mean, that's really what getting to be a scientist is, right? You get to just like play out your dreams of being a kid and just smashing things up and seeing what happens, and like, let's go out there and throw rocks at stuff and see if they explode.
Yeah, you think of the Large Hadron Collider, this big collider, that we use to try to find. I mean, effectively we smash things into other things, because in collisions you break things apart. The really good example that I remember learning years ago was, if you smash a car, and assuming there's nobody in it, the wheel flies off, the windscreen flies off, the engine comes out, and so on. So instead of just being this shaped object, suddenly you can see all the bits inside it, the seats, whatever it might be, and suddenly you can see what's inside the car by breaking it up. Now, of course, you've then damaged the car in the process, and that has its own challenges, because you're trying to think, okay, if we actually put it back together, what would it, how would it go back together? And something that's not obvious, but that's all part of the challenge. But it's by smashing things up very often, we uncover evidence that we have no easy way of doing it otherwise. So we spend a lot of money smashing things for science.
Yeah, which hopefully gives us great outcomes, though. That money's well spent. So we actually have a comment here from Colin Buckley. Thank you very much for joining us today. He said he remembers seeing the damage from Schumacher-Levy, which is quite interesting. We'll talk about that in a second, and what it did to Jupiter when it happened. And he remembers seeing it and being in awe. That was really exciting at the time. And he said, thanks, this is a great presentation. So Schumacher-Levy was a comet that hit into Jupiter. And it kind of was, from my understanding, kind of the kickstart to the idea of actually putting together a real planetary defense and making this a reality, because I've heard this described as being the shot across the bow, because that's one of our planets not that far away from us, realistically. Does anybody know a bit more about Schumacher-Levy or remember seeing it?
Yeah, I do remember it. I'm old enough, and some of the Rob and Al might have a comment, but I think you're absolutely right. I think it's a great point that's made. I mean, it was those images in the infrared showing the sort of the superheating of in a series, because as the comet came in, it broke up because of the gravitational attraction of Jupiter, and so it sort of, and you had this beautiful series of pearls of dots, which then slammed in, and you had these series of black dots across Jupiter, each of which represented a bit of the comet that had fractured. But if you looked at it in the infrared, they weren't black, they were bright, emitting, because in the infrared you're looking at heat, and this showed where they had splashed into the Jovian atmosphere and superheated, just like a shooting star does on the Earth. But it was the scale. I don't remember. Actually, I don't remember if you guys do. I don't remember how much energy, but I'm sure it was like hundreds of thousands of times the Hiroshima atomic bomb. It could have been millions. I don't know. I don't remember. We could probably should be able to remember, but I don't. But like enormous energy, and I think it's a really good example. It's a shot across the bows, as you say, because we saw it happening. Just for clarification, though, Jupiter, because it's so big, its gravity kind of dominates, and so it's inclined to attract stuff like this much more so than the Earth does. So the Earth's gravity doesn't really, make us as big a target as Jupiter. If you're Jupiter, in particular, if you're Saturn as well, you're a big target because you're a big gravitational attractor. So you kind of change the orbit of these objects, comets, or most likely at that distance. And then you get this impact. So yeah, guys, I don't know if you remember or you have any recollections of it.
I don't recall it, but as our good friend Kean O'Regan is a PhD student out at MTU, and he worked with us in the observatory for quite a while. He was a big fan of saying that Jupiter was the vacuum cleaner of the solar system, and as far as I'm concerned, that's its job. It needs to like just suck up all the stuff that could come just in the inner system. So I'm glad it did soak up the comet. I did have one question that you guys might be able to answer for me, actually, because I know the Dimorphos Didymos thing, like it's basically two asteroids, right, orbiting each other. Do you know if there's a reason why they went for that rather than a solitary one for the test? Were they hoping to impact the orbit of one around the other or something?
Yeah, I mean, I think maybe Al, if you want to take that, it's because you had started that discussion.
Yeah, sure. That is pretty much it, Rob. They wanted to see how the impact on the secondary would predominantly influence the primary, because they're so close, and because we obviously know their orbital path quite well. We also know what's called our photometry. So when we analyze them from the Earth, we know how quickly the moonlet is orbiting. It's the primary. So having a binary system that compact, but also sufficiently not too large that we'd need a massive object to make any impact. So it was just the right size, put it that way. Physically, it was the right size, had the right characteristics, but also the right orbital period, and was in the right plane for us to be able to see all of these. So it was, I suppose, fortunate in some senses. There's not that many of them that would have all of those same characteristics that we would have been able to reach in a reasonable time frame.
Yeah. So I mean, I think Al, at the minute, the pre-impact orbital period, I think, was 11 hours and 55 minutes. So I think the question now is, what does that change to? Yeah. That'll tell us how much the object is moved by. So if you think about it, the further are you away, then the longer the period it takes to go around. So what knowing whether they tried to nudge it closer or further away, I don't remember whether it was closer or further away. So they'll know that from the impact parameters. So then they'll know by looking at that orbital period that Al was talking about, whether it's, or by how much it has changed. So for example, suppose it had changed by nothing or nothing measurable, that so it's still 11 hours 55 minutes. It really means we haven't moved the object much at all. But if it changed from 11 hours 55, say, to 5 hours, and I'm being completely extreme in this, then we'd have changed it a huge amount. So that's really one of the big tests. But it's complicated because Al mentioned about bits breaking off. Now, if you start to break bits off as well, then how you interpret what you did is more complicated, because there could be those objects that bits don't break off. And so it's going to be the first test. But as Al points out, we're very lucky to have this binary system. If we didn't have a binary system, we'd have to watch the path of this object over a very long period of time to see by how much it had changed. And that could take decades to really figure that out. Whereas this way we can tell immediately, because one goes around the other 11 hours 55 minutes. And also we can watch multiples of that. So we can get an average, instead of just seeing it once, we can see it we see it twice a day, let's say. So over a period of weeks, we can really get a good idea of the new orbit and the new orbital period. And that will allow us to tell what the impact, what the influence in terms of the movement of it is, because that orbital period will only change if it moves out or in. That's what will change it. It's your distance between two objects that determines your orbital period. So if it moves around or in, then we'll be able to tell. And so, as Al said, by measuring the brightness as it goes round, you can see it goes in front, blip, 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 or is it blip, blip, that type of thing. So it'll be small, but I think they're hoping for seconds rather than anything else. But totally measurable. Well, maybe not. I don't know. I haven't seen if they've actually managed to do the data measurement on that yet.
That's actually really cool. I hadn't realized just how uniquely suited that system was to the test. That's incredible.
Yeah, it is. It's incredible that it exists, and it's just about far enough away so we can see it. And as Al says, one is just about the right size that we have a reasonable chance, we think, of moving it. And so it's like all your birthdays and Christmases coming together in terms of a target for us to test this out. And that's why we want to go back with Hera to see a little bit more closely what. So if we're still confused, then we can go and we can have a look and see, because we have the images of it from the spacecraft as it was approaching, so we can see what happened then, and then that'll tell us, well, it changed shape by this bit, so that would affect certain things, and we can wrap that into the full understanding of why its orbit has changed, and we can decouple from that any effects which are kind of secondary, like it breaking apart, for example, because we're more interested in just the impact rather than, as I said rather earlier on, we're not really. The objective of this was not to try to break up the comet in any way, or the asteroid. That wasn't an objective, but it's always a possibility. Can I just say, by the way, to go that far, whatever number of billion miles, and then to be within 18 meters of your target is just science fiction on speed. It's hats off.
Mm-hmm.
Incredible.
It's unbelievable, because you think about it, they're aiming for a spot in space when they're taking off from Earth. They're aiming for a spot they predict the asteroid is going to be in when the probe actually gets there. So like everything's estimated to be, well, hopefully it gets to that point. Hopefully all the math is right and we think it's going to be there in 10 months. Well, so it's actually amazing.
Like, it's interesting. Faster than a speeding bullet.
Yeah.
On the final approach, they actually did a secondary imager. And it was used for an auto navigation system, and it was actually using Jupiter and the moons of Jupiter as its coordinate system. How they related to each other would tell it how accurate it is in relation to the actual asteroid. So it actually had its own navigation system, a stellar navigation system.
And I think, Al, it had to use artificial intelligence because it's too far away to make any last minute adjustments from any Earth command. So it needs to do this all autonomously, and everything. The spacecraft was on its own type of thing in those last.
The last 5 minutes were pretty much
the last few minutes in particular. Yeah,
we're basically it's out of our hands. It's now completely automated, To paraphrase what ground control said, they'd never been so happy to have lost the satellite signal in their lives.
I was listening to the planetary defense officer for NASA, who is involved in this project, and he was saying that exactly it's too far out, that in terms of the speed that it was traveling at and the way that we would be able to communicate, we wouldn't be able to joystick it in. So it really just was relying on everything on board and all the technology and everything. So it's amazing that this mission has even happened. It's absolutely, and exactly what Niall said, I was going to actually wrap it up with this, is that this is truly science fiction. The stuff right out of science fiction happening out in space through all of the space and technology and math and everything that has been going on in the space industry and the space agencies right now. So it's amazing to see what's going on. And hopefully will help us all live life here on Earth for a long, long time, because we'll be protecting Earth with all of our asteroid diverting technology that we've got.
Too late for this guy, unfortunately.
Luckily, we're smarter than them. So any last comments here on the missions and asteroids? And I'll give everyone, go ahead, Robbie.
I think that I just want to kind of follow on from Niall's comment that it feels like a kind of a new golden age for us. I feel like the Apollo era for space exploration was a really exciting time, and there was always really cool stuff happening. And this week, it really drove home for me how much cool stuff is happening with like the Artemis mission and with this mission and like all these other missions that are planned or kicking off or just after wrapping up. And the scale of what we're doing just never ceases to blow my mind. And as Niall says, there's a sci-fi comment that really drove it home for me. A couple of years ago, there was a Star Trek movie starring Simon Pegg as Scotty. And he referenced something being as difficult as shooting a bullet at another bullet while blindfolded, riding a horse. And it genuinely feels like that's what we're pulling off with stuff like this, hitting things so far away from us that, as you said, we can't fine-tune the last moments of it. It is just a massive testament to the teamwork that goes into these missions. It's incredible stuff. It's really exciting.
And maybe my last sort of comment was that this also allows us to, and we saw it with the Phoebe lander on Comet 97P.
67P, I think.
87P,
I think.
67.
Do you know what? Like, that was totally ingrained in my mind, for so
For
long.
so long.
And
That's
now,
all we talk
and I was like,
about.
oh, hold on a minute. I never wanted to use the actual total, the full name of it, because it just, I could never get the pronunciation right. But we've landed on a comet. We've now smashed into an asteroid. But, we're on the cusp of being able to see how we can use those maybe to help us going forward as resources, to either if we're going, on interplanetary missions, or maybe to replenish material on the Earth that is used up, and without damaging the Earth, and without indeed using these as kind of, natural high sources of very high density of some very precious minerals and so on. So I think there's so much going on at the minute, and for me, it is absolutely, agree with Rob. It's a golden era, and it's a golden era where increasingly the likes of countries like Ireland are involved. So we're less and less. We often say this, if you listen to the live streams previously, we're less spectators now and we're more involved. And so I find that very exciting because, let's be honest, it is nice to be a spectator, don't get me wrong, but it's also nice to have some involvement, and increasingly to have a bit more involvement. So it's just a great time. Space Week's just a great week.
All right.
Yeah.
This is your last chance to ever talk about DART ever. This is the last comment. Final comment.
Yeah, no, it is. I mean, the mission from an engineering point of view and from a scientific missionary point of view is just, unbelievable. It's a fantastic achievement by all involved, and it will pave the way, irrespective of the results of this. It will pave the way for the next future generations, but also future missions of this type, because we're going to learn so much from this. Irrespective of the results of whether it did manage to move it, whether we even catch whether it moved it or not, we've learned a whole load of information just in the engineering and science point of view already, that it's going to impact, pun intended, the next number of missions that are going to be going up there. I do think as well, in the wider context, so DART itself launched its own CubeSat. Hera, when it's approaching the binary system, is going to launch 2 of its own CubeSats. So we're now in a generation where we're not just launching a satellite or something like that to a mission to go there. We're actually launching multiple satellites, multiple missions, all within each other, to go somewhere, cool. And then diverse, and then so there's ample opportunity. And these CubeSats are very small, 10 by 10 by 10 centimeters cube, so they're quite small. There's ample opportunity for everyone to get involved in these type of missions at some point down the line, and to see what's going on. So it's a very, very exciting time to be involved, and there's going to be more and more of these missions going forward. So it's a very exciting time.
Yeah. It's very, very exciting time in space. Loads of missions happening. The September was just like everything. We watched NASA TV all the time in labs, and it was like every day there was something new, and they were cutting into other launches. No, wait, I would love to have talked about Artemis. I didn't even bring it up because this would be hours long, and I think YouTube does have a limit for how long we can actually talk on here. So, but I just want to thank everyone for all of their input today. And thanks for joining us for the Asteroid Chat. Thank you for the viewers, and thanks for your questions. And I really enjoyed this. I hope everyone is enjoying Space Week 2022. And if you're looking for ways to get involved, you can go to spaceweek.ie. We have our events registered there. If you'd like to register your own events, you can do it there as well. But thanks so much for joining us for this live stream. And we sure will be doing this again. So join us for future events. Don't forget to subscribe to the channel, and have a fantastic Space Week 2022. See you all very soon.